In this section, we're going to look at vector functions and space curves. Now, we've already looked at vector functions and space curves, but we only looked at linear ones. So an example would be, this picture you see here, or that's given by this equation or set of equations here parametrically. Also written down here in its vector function form. So we understand that when we have a parameter t, and we have functions of t that determine x, y, and z, but then those functions of t are just linear in the variable t, that should just form a line in 3 space. So what we're going to do now is broaden our horizons and talk instead about functions that may not necessarily be linear, like this one in example 1 here. But before we look at example 1, let's just kind of understand what we're looking at here. So one of the things we can do is just kind of open up our 3D grapher here, and what we want to look at for the most part here are space curves. Okay, so you can see it's r of t, so x, y, and z all depend on t, and we saw this when we were working with lines before. And so that picture from the top of our notes there, if I type in those same expressions for x, y, and z, not surprisingly, we get just a line. Okay, but what if we kind of spice things up a little bit? How about we make x into t, y into t, but then we said z could be t squared. Okay, well, not surprisingly here, we get a parabola, right? In 3 space, because we have this whole taking the x and squaring it, that idea, right? And also, I guess, taking the same as the y value and squaring it. And so we get a non-linear space curve here. Or how about this one? Let's say I did the cosine of t, the sine of t, and t. Okay, if I did that, what I get there is, a helix. Okay, and this makes sense because one of the things you might remember from when you first learned how to parameterize curves is that if you want to make a circle, you just make the x value the radius times the cosine, and the y value the radius times the sine when you're in 2 dimensions. Well, if I look down just on the xy plane here, what do I essentially see? I just see a circle, right? And so, but now that I add a z component that's equal to t, the idea is the bigger t gets, the bigger z gets. So we get that circle action, but then it's also climbing, right? So, so it's actually, if we kind of break it down, it's not surprising that we get this helix here. All right, so now let's take a look at this, this vector function that we have here. It asks us to find the domain of this vector function. So just like we have to be careful of things like not dividing by square roots, not dividing by 0 and not taking the square root of a negative number, just like we had to worry about that with regular single variable functions, we got to worry about that here. So we check for the same sorts of things. So in my x component, I can see that it's important to make sure that t is greater than or equal to 0. But then in the z component, I can also see that t to the negative 1, that's equal to 1 over t, right? And so we also know that t should not be 0. And then we'll just note that, e to the t, really nothing can go wrong there. It has no restrictions. Now, even though these are 3 different functions for x, for y, and for z, we have to put all of this information together. So while it might be okay to put a 0 here, it wouldn't be okay to put a 0 in for t in the z component. And so we basically combine all of these and say, well, t's got to be greater than or equal to 0, but it also then can't be equal to 0. So that means our domain is t is greater than 0, or 0 to infinity non-inclusive. So these vector valued functions have domains just like functions of a single variable do. All right, now one of our goals over this section and the next section is to understand how calculus can be done on these vector valued functions. And so the way we're going to start here is with the limit. That's how you start in Calc 1 when you start to study calculus, is to look at limits. And so let's do that here. So a limit is defined as you think it might be. So if you have your function r of t and you have f of t giving you your x, g of t giving you your y, and h of t giving you your z, then to take the limit of the vector valued function, you're just taking the limit of each individual component. So what I can literally do here is, in example 2, I can say, let's take the limit as t goes to 0 of this that minus sign a little lower. But that's just going to be equal to the vector, that is the limit, as t goes to 0 of 1 over t plus 1. The limit as t goes to 0 of e to the t minus 1 over t, and then the limit as t goes to 0 of 4t. All right, so we just take each individual limit. Now you can see that in this one, there's no problem. As t goes to 0, the x component definitely just goes to 1, right? Sorry, that should be 0 there. But it goes to 1 overall. Now here what happens though is if you let t go to 0, then the top goes to 0, but then so does the bottom. So that's, remember, an indeterminate form. So remember, what we want to do here is apply L'Hopital's rule to see which one of these basically wins out. So this is going to be e to the t on top over 1. Just make a little note, L'Hopital's rule. But then the third one's easy, right? Let t go to 0, the z component's going to 0. Okay, so now can we make sense of this? This is a 1 here. If t goes to 0, that's e to the 0 over 1, which is 1, and the z is 0. So what we're saying here is that if you take the limit of this vector valued function, it's heading toward 1, 1, 0. But understand that when you can't actually plug 0 in here, can you? Okay, so it's this idea that we can still talk about where this function is going, even though we're not allowed to have t be actually equal to 0 in this case. All right, I like this visual here. One of the things you probably remember from when we were studying lines is that I like to think of what the function itself is doing. What the r of t is doing is the r of t is like the vector that goes from the origin up to whatever point you're at, and it's kind of like the pencil that is tracing out the curve. And so the same analogy applies here. So if you're at a particular point, you can find that point by just plugging the appropriate value of t in for the x function, the y function, the z function, right? And that is just also saying that we have the vector r of t going from the origin to that point. All right, so in example 3, we're going to try to take a closer look at an example of a space curve. And one of the things we'll be interested in with space curves is sometimes we'll be interested in, do they lie on top of a surface? All right, so we're given this space curve r of t, given by that function here, and we want to know, they want us to show that it lies on this cone. Okay, so maybe this is a good one for us to start by looking at a picture of this. Let's go ahead and graph it. So it's kind of similar to this one. But it's t times the cosine of t times the sine of t. That might look kind of funny. Let me graph some more values of t though. How about we go like negative 15 to 15. Okay, and whenever things look kind of herky-jerky like this, what you might want to do is increase your discretization. So I'm going to go up to 100. That's just maybe even higher. Let's go like 200. That looks better. So kind of interesting what we got here. So they're asking us, does this space curve lie on top of the cone they gave us? Well, maybe so. I mean, it kind of looks like you could fit a cone, in there, and also the downward facing part of the cone in there. So seems plausible. So let's go back and talk about how we show that. So the thing to remember is that this is an x, this is a y, and this is a z. So if we can show that the relationship amongst x, y, and z in this curve also obeys this relationship here, then I can say that yes, it does in fact lie on that surface. All right, so let's start with the right side here. So we have x squared plus y squared. Now, my x, according to the space curve here, is given by t times the cosine of t. But because the x was squared over here, I'm going to square that. And then I'm going to add, instead of y, t times the sine of t. I'm going to square that. Okay, and then what we want to do is simplify this and see if we can make the z component, t, appear. So I can distribute my square through, so this would be t squared times the cosine squared of t plus t squared times the sine squared of t. And okay, yeah, we see the t there, that's our z, but we got a lot of other stuff here. But hopefully you're recognizing, our best friend from trigonometry, which is whenever we have cosine squared plus sine squared, that often bails us out of some complicated expressions. So if I factor that t squared out, then I just have cosine squared plus sine squared, which of course we know is equal to 1. Okay, but now what do we know? We know t is equal to z, so this is equal to z squared. So what I've been able to do here is show that this space curve obeys the relationship x squared plus y squared equals z squared. All right, so that's all. That's all I need to do to show it. Now, it might be nice to actually graph this and see it visually. So let's just remember that when you have something like z squared equals x squared plus y squared, we do, in order to use our grapher, need to get it in function form. So z equals something. So on the computer, this z squared equals x squared plus y squared really yields two different functions. Z equals the square root of x squared plus y squared. But then if you take the square root of both sides, it could have equaled the negative square root of x squared plus y squared. So I'm going to go ahead and graph both of those. And what I'm hoping to see is that when I do graph those, that cone that's generated perfectly is holding that space curve. So here we go, the square root of x squared plus y squared. And and obviously that's just a small part of the cone. I kind of want to match what I have going on up here. So my x's and y's look like, a little past negative 10 to 10. So I'm going to go negative 15 to 15. I think that was kind of coincidentally the t values that I used. And then to make this a little more refined, see how it rounds off at the bottom. We know cones don't do that. Let's make this discretization more precise. So that looks pretty good there. It looks like that curve, when you see it dotted like that, that means that that curve's lying right on that surface of that cone. And while I don't think there's too much suspense anymore, let's go ahead and graph the lower part of the cone too. Of course, change the X and Y bounds and the discretization to match what we did above. And same thing. So we can pretty safely see there that the cone holds this space curve that we were given. All right, now we kind of cheated. We used technology to come up with the graph already. So I still want to do this exercise here, though, where we are trying to sketch this curve and show that it, in fact, does lie on this cone. And so let's go ahead and do this. So first thing is let's make a list, or a table, I should say, of different values of t and what points those generate. So we understand that if I plug in certain values of t, that's going to give me a particular x, y, and z value. So it's going to give me a point to plot. So if I plug in t equals 0, then, since I don't have it on the screen right now, let's rewrite it here. R of t is equal to t cosine t, t sine t, and then t. That's, of course, going to be the point 0, 0, 0, right? Nothing too special there, so I can just put a point right there at the origin. Now let's be smart about this. We want to have values that are going to spit out nice things for us, right? And in fact, it would be nice if I could plot kind of in places where it's easy to graph. So maybe along the positive y-axis, the negative x-axis, the negative y-axis. So we know that we'll be at the positive y-axis at pi over 2. Okay, but if I put pi over 2 in for cosine, that's going to be 0. So that zeroes out my x. But if I put pi over 2 in for sine, that's going to be 1. But then I'm going to have pi over 2 in the t as well, so that's going to be pi over 2. And then, of course, pi over 2 in the z. So what I want to graph here is make a notch, and this is going to be pi over 2. And then here, same notch, pi over 2. So that's going to give me something like that, right about there. I know it looks like it's on that negative x-axis, but it's not. It's elevated a little bit. All right, so now let's try pi, right? That would be the negative x-axis. So when I take the cosine of pi, I get -1, so that's going to be negative pi. The sine of pi is 0, and then pi. So I'm going to go up pi here, and I'm going to go, here's negative pi over 2, here's negative pi. So we'll have something like that. And then let's try 3 pi over 2. So that's going to give me a 0, because the cosine of 3 pi over 2 is 0 for the x. It's going to give me a negative 3 pi over 2 for the y. It's going to give me a 3 pi over 2 for the z. So negative pi over 2, negative pi, negative 3 pi over 2. And then here's 3 pi over 2. So it's going to give me something like that. And then finally, if I go over here to, let's see, let's go ahead and wrap it all the way around to 2 pi. So if I do that, the cosine of 2 pi is 1, so that's going to be 2 pi here. It's going to be 0 in the y, because the sine of 2 pi is 0, and 2 pi in the z. So this is going to be here, and then 1, 2, 3, 4. And so I will go right about there. Okay, so this is a little bit tough, right? How do I connect all this up? Well, I know it's got a spiral, and it's all got to be contained in a cone. So one thing that might be useful to us is to now make a cone that goes out from -2 pi to 2 pi in both directions. So what that means here is that I better do this in a different color. Let's do this in green. So I'll come all the way out here to here where I think about 2 pi is in the y, and then back here, I'm going to go ahead and erase this now because I need the space, and then kind of come back this way -2 pi there. I already know that this is the spot I want right here for this edge of the cone, and then back here -2 pi, -2 pi. And so what I'm going to do is, of course the top of the cone is going to make this circle. So I want to make the circle that's forming the top of this cone best I can. And then of course I know what the cone should do. It should come down to the origin, right? From here it should come down to the origin, but it's kind of part of it's hidden there. And the rest of it I can't really see too well. All right, but now I can go ahead and graph the spiral, right? Remember, I'm going to finish it up here. And so hopefully when I'm done with this, it'll give the impression, at least, of lying on that cone. And I can already see I don't really love this part of it right here, right? So if I was going to be real picky about it, I'd probably erase this, do a little bit better job of making that seem to trace along. So that would kind of entail going a little more back like that, and I already like that a lot better. And so you can imagine here this space curve lying right on that cone. And maybe to kind of give that cone a little bit better definition, I could kind of do something like this, right? So this is, so at each point you can kind of see heading right down to the origin. All right, so let's do one more example. So this one's interesting. This one gives us a couple of surfaces to look at, and then it wants us to find a vector function that represents the curve of intersection for these surfaces. All right. Now this one, I think I'm going to have the picture lead us here, as opposed to the algebra, just to kind of attack it a little bit differently. So if I'm going to let the picture lead us, we got to figure out what these things are. So first of all, let's start with this one. This one's interesting because it's missing the z. But remember, when it's missing the z, that means that x squared plus y squared is equal to 4 for all z, right? So that relationship with x and y exists for all z. So let's start with z equals 0. It's x squared plus y squared equals 4. That's a circle, right? This is a circle of radius 2 for given z values. So you freeze z in place, you're going to get yourself just a circle. So I can definitely easily sketch that here. Right, circle of radius 2, pretty easy to make a sketch of. I'm going to keep it kind of light, because I don't know yet exactly which parts I kind of want to be hidden and which parts are going to be really prominent. So I'm just going to keep it light. But then that's got to be the case everywhere. So if I went up a number of z values, okay, then the same has to be true way up here. So just take this as an example. If I go straight up and try to stay kind of parallel to the x-axis, that same point would be about there, parallel to the x-axis. That same point would be there, and then something like that, and just below would be something like that. And so, you know, up here we also get another circle, and that would, so now we can kind of see this thing starting to take shape, right? So then connecting up some of these, and of course this thing does go down below also for sure. I just for now just trying to get an idea of what this thing looks like. All right, so this thing of course is just a cylinder. All right, and I'm not really that happy with what I've got graphed there. That's not great, but that's okay. Just trying to get a ballpark of this for now. Okay, so there's my cylinder. Okay, now what about this other thing here? What's this? Well, anytime you're able to get z by itself, that might be a good place to start. So if I just add 1 to both sides, I can see that z is equal to x squared plus y squared equal, plus 1. Plus 1 is what z is equal to. So remember, if you're unsure about what to do, sketch traces, right? Sketch traces. So if I do some traces here, how about the trace when y equals 0? Well, then z equals x squared plus 1. Well, we know what that is, right? X squared plus 1 is just a parabola that's been shifted up 1. So it's got a y-intercept of 1. And so when y equals 0, it's going to go over 1, up 1, over 1, up 1. When it goes over 2, which is where the edge of the cylinder is, it's going to go up 4. So that puts me right there, right? We did this at z equals 5. When I go over 2, it's going to go up 4. That's going to put me right there. So this is going to be a parabola. And by the way, I know I kind of cheated there. I know I kind of cheated by having my cylinder stop at 5. I admit I knew that that's where they were going to touch. So sorry about that. That was a bit contrived. But let's go ahead and then do the trace for when x equals 0. Then you get the same thing, right? But it's just y squared plus 1. So now we just, over 1 on the y, up 1. Over 1 on the y, up 1. Should be a little bit lower. Over 2 on the y, up 4. Over 2 on the y, up 4. And so you get another All right, and then, so what are we getting here? We're getting a paraboloid. Finally, it kind of looks like everything's intersecting here at z is equal to 5. So let's also trace when z equals 5. Then you get 5 equals x squared plus y squared plus 1. So we subtract 1, so we get 4 equals x squared plus y squared. So we know that when z is equal to 5, we just have a circle, right? A circle of radius 2 being drawn when z equals 5. So in fact, that top circle there should be the place where these two surfaces intersect. Okay? Now we're far from done. We just drew a picture here, and I admitted that I kind of knew ahead of time where I was going. So it kind of probably gives a bit of a false sense of how easy it is to come up with the place they intersect just by sketching the surfaces. It's really not easy. So So I apologize for cheating. Okay, but we can definitely show this. It's not just about sketching it. We can do this algebraically. All right. So remember, at the intersection, right? At the intersection, both equations must hold for x, y, and z. So what does that mean? That means that if I know that x squared plus y squared always equals 4 for this equation, then that means x squared plus y squared has to equal 4 for that equation also. So what I'm going to do here is, first of all, let's just number these equations. So I have x squared plus y squared equals z minus 1. That's equation 1. Equation 2 is x squared plus y squared equals 4. But what I'm going to do is, because I know they have to both simultaneously be equal when they intersect, that's got to be 4, because x squared plus y squared is 4 in equation 2. So z minus 1. So how did I know ahead of time really easily that 5 would be the magic z value? Because that's what has to be the case if both equations are true at the same time. Okay. So that actually gives us part of the answer. Because what did it ask for? It asked for find a vector function that represents the curve of intersection. So understand, when they ask us to find a vector function, we need to give an answer that looks like this. Right? So part of the answer is done. I know I got to put a 5 here. There's no question about it. Okay. We also know that at the intersection, we have a circle of radius 2. Now, this is going to ask you to dig back a little ways. One of the facts that I want you to remember, it's going to come up enough in this class and in Calc 4 that you should just remember this. But if you, and how do I want to say this exactly? In R2, so when you're only talking about 2 dimensions, a circle of radius, we'll say A, centered at the origin is, and we'll call it V of t, to not confuse with what we have going down here, is A cosine t, A sine t. All right, and you can prove that to yourself by again showing that it satisfies, just like in the last problem, it satisfies x squared plus y squared equals a squared. If you plug these in for x and y, you get a squared. Okay, so what that means is, since we have a circle of radius 2 and it's centered at the origin in terms of x and y, right, when x is 0 and y is 0, then the x and y components are given by 2 cosine t, 2 sine t. And this idea of constructing a circle in this way, it's going to happen enough in this class, and it's going to happen enough in Calc 4 that you just need to have that one in your back pocket, right? Whatever the radius is, get the x by multiplying by that by cosine t, get the y by multiplying that by sine t.